hopefully everyone comes on Monday, right? So welcome, hello world, class of 36. That is now. Some folks will probably stroll in over time here, but let's just put a big welcome to Physics 221, right? So the first of a three-quarter sequence on physics here at Seattle Central. This is our virtual classroom. Let me kind of quickly introduce you. We got a whiteboard over here and whiteboard over here. Oh, with an equation written here. We don't need that one right now. Cool. But what I wanted to do, well, eventually, actually, and we have a little lab station over here. There's like wires and some stuff. There's junk. I'll clean that up later. But for now, we got kind of our two whiteboards here. And we'll just kind of like scan here, look at all this stuff. Okay. So what I wanted to do first was just take a quick look through the Canvas page and just show you all a few things. Probably spend 10, 15 minutes looking at that. And then we'll just kind of jump into, I'll talk a little bit about chapter 1, and then we'll jump into chapter 2. Okay, so I'm going to hit the share screen button and change cameras here. Oh, wait, let me get this going. This will just take a second to hit the share. Okay, now I go back over here. And then I hit share screen, and then I hit this button. And here we go. And let me change cameras, because when I'm looking at the computer screen, here we go. This one kind of makes a little bit more sense. There's a little bar here in the way, but this classroom is a little bit in the works, right? So, but this bar doesn't bother you guys too much. Okay, I think this is fine. So let's just kind of do a quick run through of the Canvas page. If you've taken a class from me before, it's pretty similar. Here's blah, 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 this stuff here, right? Wednesdays, 6 to 8 will be the optional live. Mondays, 6 to 8 in the Zoom room. That's when we'll be doing our labs, virtual labs / tutorials. Wednesdays, I'll be doing a live session from 6 to 8, like a 5-minute break. I need to drink water or something during that time. And I'm going to be posting some additional videos that I just film at random times. And the things that I do on Wednesdays and those other videos will all be posted on Panopto, right? Which is like, okay, well, I'll put Panopto up here. Panopto is not on there right now. It'll appear over here. As I haven't made a video yet, so I haven't made a Panopto thing. So you'll see Panopto here on the left. But anyways, that'll just take a minute. First, let's just take a look here. I just want to show you all, this is our schedule, right? Blah, 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 blah. You know, you can take a look here, our labs, and it's a tentative schedule. Things might change a little bit with what chapters we'll be covering, units and significant figures, kinematics. We'll mostly be talking about kinematics in one dimension today, not as much on this units and sig fig stuff. You can download the notes, right? Like if you click here, you'll see this is a PDF. I recommend printing it. Even though you're like virtual world, whatever, you can print this and take notes on top of it, right? So, and just kind of like having a physical copy is kind of nice. So you can peruse through that. And there's like what labs we're doing, et cetera, et cetera. Okay, let's go back to the home screen here. Excuse me. All right, there's my name, Jonathan Erson. You can call me John, Johnny, or Jonathan. Most people at Central call me Johnny, so whatever you want. Hey, you. Email, office. I should get rid of that because I'm not going to the office. I do have office hours in the morning for my morning class, and I did not go to my office hours today. I guess maybe I should have just in case. Oh, that needs to say Monday 5 to 6, not Tuesday. I need to fix that. But Monday 5 to 6, I'll have office hours. Syllabus is pretty much the same as what we'll see here. There will be labs. Okay, so we're going to have a variety of labs. Some are going to be like handouts, activities. Some you'll be making measurements, looking at the video. Some I have one activity where you're going to make your measurements by printing or just using a ruler on your laptop screen, right? So you will need a ruler for the lab in 2 weeks. If you don't have a ruler, you could print a ruler or just talk to me if you don't have a ruler. We can figure something out. It's not that big of a deal. Homework. Okay, I noticed like maybe 7 or 8 of you have access to the homework. It's at Mastering Physics. Go to masteringphysics.com, I think, go or click there. You'll need to buy an access code. Oh, I can't remember. I think it's like 150 bucks or something like that. And that will last you all 3 quarters at Central for Physics 1, 2, and 3. And for the online homework. You can pay a little bit more and get access to the ebook. That's also an option. Some people buy the smaller amount. And then I didn't say this, but I think you can Google the PDF of the book and not have to do that. I know people do that. It's discouraged, highly, highly discouraged. But I know people have done that in the past. Here are our exams schedule. You'll see October 26th. We will have on the week before this, October 26th, we're going to have a practice exam because I don't want to have the actual exam be like so like what are we doing? The way it's going to work for the practice and the real exams, I am going to email you the test as a PDF and a Word file. Download it however you want, and you can print it out and scan and send it to me, or have it open on your screen and work on a blank sheet of paper. Now, what you will have to do for the exams is have a webcam that kind of just shows your work area and that you're not accessing, your phone or some stuff like that. We will have a practice exam, like I said the week before, where everyone needs to show kind of like what their setup is for approval. And then, that way on the actual exam day, you can just replicate what you did on the practice test. So that'll be, I guess, the 19th, which is a week before the 26th. Whatever before the 26th is, the Monday before. Grading, blah, blah, blah. The book. You'll also need, this book here from the bookstore, or I know people pass around a PDF of this. Let me grab it. I have one version, there's 2. This guy here, all right, if you go to the Seattle Central Bookstore website, you can order this guy, and this will be how we do some of our labs, right? Some of the labs will be from that book. Obviously, you need a calculator. Oh, if you click here, this is pretty cool. Here's all the tutoring available on campus. I'll open it. I'm gonna switch screens here. Okay, let's see, new share. Boom, look at this. Okay, so here's the DE Learning Center. I guess if you're taking Arabic, there you go. But there is still tutoring for statistics, math, accounting, some of this stuff. Oh, here we go, physics, SAM Learning Center, right? So here's the SAM Zoom link. And if you go to the web page here, I'm sure it tells you more about how the tutoring works. But super helpful, right? Even though we're in this weirdo pandemic like virtual world, the SAM Learning Center is still open, kind of the same way this class is probably operating on Zoom. So check it out. Take advantage of the free resource. Let's go back to Canvas now. Am I recording? Wait, I should hit, I don't think I'm recording. Where's the record button? Hey, where did, I'm gonna hit stop share for a second just so I can push. Oh no, I'm recording. Stop recording, okay. I thought I wasn't for some reason. I don't remember pushing start. Oh, and it says up there recording. Okay, we're good, we're good. Okay, some stuff, you know, the alerts. I guess like we can't really have a snow day, can we? You know, like usually we can have snow days, but no snow days this quarter. Some links I like, it's books I like. You can check that stuff out. One other thing out of here, discussion forum. There's a little intro thing that you can check out. It's worth some points in the participation. So check that out. Just has some light questions. Maybe we'll head over there. You know, like what's your dream job, blah, blah, blah. A lot of people have already answered. You can reply to each other. So check that out. And there's another thing in the discussions. I'm going to have a video on Monday on this too. We'll watch a video in class. The NCAS 2020 is accepting applications. Free trip to Space Camp. So if you click here, there's a flyer. I'm not, click it. I don't know if it'll open. Anyways, but people have done this from Central in the past. And what it is you apply for this program. And if you get accepted, you are enrolled in an online course. It's always an online course, even in non-pandemic times. Oh yeah, NCAS, NASA Community College Aerospace Scholars, right? And there's these info sessions that's all, and you can go to that link. And yeah, you do this online class and there's like one of those online communities, you talk to each other on the discussion forum. And if you do well, people get a free trip for like a couple days to go like do stuff with NASA engineers. So I've had several students, you know, move on and participate in this. So it's not like, oh, some students, you know, move on, you know, like, you know, someone wins the lottery, you know, but I've had people participate this like many years in a row, not just like one student who got lucky, but year after year, some years like 2 or 3 students from Central have gone. So, you know, it's very realistic that you do well with that online course that you could get selected. You know, it's not a impossible thing. So check it out, NASA Community College, it should be NCC, I think, whatever. And NASA Community College Aerospace Scholars, right? So check it out. If you need me to be a reference, I'll be a reference. I don't know if you need a reference for it or not. Anyways, so that's that. Let's hit this. Let's go back to home. I think that covers everything. So I'm gonna hit stop. Oh no, there's one other thing. Yeah. Let's go to Mastering Physics. Go over here. I just want to open up the calendar real quick. Sign in. So this is Mastering Physics, and yeah, some other courses. Physics 221. Oh hey, look at this. That's cool. That's better. Ooh. All right. We wait. And I want to go to calendar and mention a few things. Cool. All right. So you'll see a calendar that looks kind of like this. That's today. On Saturday is the first assignment, Intro to Mastering Physics. It's just one of those like, how does mastering physics work? You know, like, yeah, pretty easy peasy. And then here, I'm not going to lecture on chapter 1, significant figures and units. The online learning kind of thing is going to be just like doing this guy here, this module. Here, if we, I don't know, if you want, can I open this? Oh, something in the chat. I think that's the right book. Yeah. I think you got it. Okay, closing the chat. Let's see, math skills. Oh, there's student view here. Oh, another thing in the chat. It's like a turquoise book. Oh, I only know of one edition, so I think it's the first edition. Yeah. Is there 2 editions? I think first edition, yeah. Okay, student view. Just waiting for this to open. Anyway, I'll talk. We don't have to look at it. I don't know if you can even see this thing. Let me make sure I'm sharing the right thing. Here we go. Share this. Boom. Okay, so here we go. This is module 1, chapter 1. I'm not going to lecture on it, but it's all just about like converting units and some significant figures stuff. And there's no harm in guessing. You know, you have unlimited attempts for this. So you could kind of just like do whatever and, you know, like do it wrong. Like, oh, 1 hour equals 60 seconds. And you kind of like, it says like, how sure are you? And you're like, I am so sure 1 hour is 60 seconds. Oh, and it says you're sure and incorrect, right? And based on your responses, it kind of adapts and makes you come back to stuff that you might need to review, right? So there'll be a few things where you learn the material this way. You know, I won't be doing the online lecture for it. It'll be just kind of like, you know, learn on your own using the adaptive learning module. But I'll definitely be able to answer questions on this stuff. But I kind of am only doing that for like a couple of the chapters that I think you'll be okay. You know, the units and the sig fig stuff is not too bad, right? I think our time in lecture, in this Zoom lecture, is better spent on chapters 2 and 4 for this first part of the quarter. Okay, blah, blah, blah. Let me, let's see here. I'm gonna do another new share. This is exciting. Oh, I see another chat. It's flashing and I'm going over to the chat. So it is kind of like, it is kind of like Alex. Yes, it's very much like Alex. I'll put that in chat. Yep. Oh, it was a private message. But it is like Alex. Someone asked, is it like Alex? It's very similar in that way. Okay, let's go back to this calendar. Where did the calendar go? Maybe I have to get back. Oh, sweet. Calendar, here it is. All right. So yeah, so you'll see this math skills module, and then the real homework here, chapter 1. For the real homework, some of these modules, you have infinite guesses, and you can get, it's kind of like learn. I did one for this 1D kinematics too. But the homework, like chapter 1 homework, let's do student view for this. I think it's worth looking at. Wait. Oh, okay, let's see. Yeah, we want this guy, move over here. Right, for this guy, you do not have unlimited attempts. You have like 5 attempts and you kind of get like a docked point each time. So, oh, let me hit the chat. The homework is not timed. It was asked, but you do not have unlimited attempts. So it's not like the learning modules. So you want to like really do the problem. You don't want to sit there like guessing and checking like, is it 2? Is it 3? Is it 10? Is it 20? Is it 100? Is it 200? Negative 200? Because you'll blow through your chances. So don't do that. Okay, cool. Let's okay, so well, here's the homework. Here's the first one. I'll close this. I'm gonna go to whoa. How many chances for each question? Oh, I just closed it. It says on there when you open, I think it's 5, but I always I think I can go over here. Yeah, let me check. Let me just double check. I hate saying what it is because it's one of those like you teach like 3 classes and like each thing has a different thing, and so I just gotta look. 6 attempts per question. It's 6 attempts per question. There we go. Okay, that's one of those things you have to look up though, right? Because I guess I don't do the homework, right? I mean, I did it at one point, but that was a while ago. So yeah, not as familiar. Cool. All right, I'm gonna switch cameras back to this guy, the classroom camera. Hello. Oh, and let me get this. So right now, this thing is a little busted. I gotta just like move it by hand, but it's eventually gonna be something that like follows me, right? And we're gonna have more whiteboards. Right now we have 2, right? Then you go over here and look in the closet, it's just like messy closet, whatever. But well, I mean, I'm gonna put another whiteboard here and it'll like live follow me. I just have to kind of like get that squared away. Oh shoot, this is the wrong piece of paper. The right piece of paper is over here. Okay, so what I'm going to do is at 6:20. Let's talk. I want to talk a little bit about chapter 2, like I said. I'm just going to kind of lecture here. My recording, yes, about chapter 2, and maybe give a little bit, maybe before even chapter 2, just talk about the whole quarter, right? I want to just give you a quick what we're coming up to, right? So the first exam is chapters 1 through 4.
Sorry, can I ask a quick question?
Oh, yeah. Ask away.
Sorry. So it looks like you listed 2 books plus the Mastering Physics. Is that correct?
Let's see. There is the...
So there's the tutorials in introductory physics.
Yes. Yeah,
and then there's physics for scientists and engineers.
Yeah, the tutorials and then night physics for scientists and engineers, 4th edition, correct.
Okay. So there's 2 versions of tutorials in introductory physics. Does it matter which one we get?
Are you talking about how there's a tutorial and then a homework tutorial?
No, there's tutorials 1st edition and 2nd edition.
Oh, 1st edition and 2nd edition. Let me peek at, I think it's going to be...
I think that's what I was asking because mine just has physics. It doesn't have engineering in it.
Yeah, let's see here. I did not know there was a 2nd edition. I might have to inquire just to make sure. Oh yeah, 1st edition. We have 1st edition here, right?
Okay.
Yeah.
Okay.
Yeah.
So then those are the 3 things that we need to get, just so that I have that clear.
Exactly. Yes.
Okay. Great. Thank you.
Yeah. No problems. Oh, and who was asking the question?
And
it's Vamsi.
Vamsi. Oh. Nice to meet you. And who?
Yeah, and then I think Carmen was also asking.
Okay, Vamsi and Carmen. Cool. Good to know. Yeah, I still want to know you guys. It's like cool. Oh, and yes, 3. So there's like the, I'll hold it up. Oh, whoops, walked into that. So there's this book, right, which you can get as an ebook, right? And I don't assign anything out of it. I recommend reading it. Some people download it as a PDF. But there's this book or the ebook version. And then there's 2 books. They're like this. I have another one, but I'm going to have to dig around. There's this and a very similar one that just says homework on it. And so like this is like the lab. And then there's a homework that goes with each of the labs here. Cool. All right, so put this back. Okay, so overview of the quarter, like I was saying. Let's talk about that. Chapters 1 through 4 is kind of, okay, there's like units, which is chapter 1, but it's mostly focused on what we call kinematics. And maybe I'll just call that objects in motion, right? That's kind of the main idea of kinematics is we're just talking about objects in motion. It's like, for example, a great kinematics question is a train leaves the station at 5 p.m., heads west at 85 miles an hour. How long does it take to get to Cincinnati? You know, of course, that's like, you know, which is like however many miles away. That's a pretty simple question because it's like the train is moving at a constant speed, you know, assumed, let's say, 85 miles an hour. But you can imagine, and this is what we'll learn in, in chapters 2 and 4, what if the train is not moving at a constant speed, right? It starts off slow and then gradually speeds up. And you can imagine lots of different scenarios similar to that. But it's just talking about like you might know the speed, how long does it take to get somewhere, or you know how long it took to get there, what's the speed, and various versions of questions like that. So that's kind of chapters 1 through 4. And we'll be dealing with chapter 2 is one-dimensional motion. You know, things that are just going to get either going up or down or left and right. Chapter 4 is motion in 2 dimensions, right? So something that might, dropping everything, something that might be moving, you know, left and right as well as up and down or in a circle, right? 2-dimensional motion. Cool. Then we get to chapters, I think it's 5 through 8. Right, chapters 5 through 8 deal with forces and Newton's laws. Cool. I'm going to adjust this just a tiny bit. Cool, perfect. Okay, so forces and Newton's laws. And kind of the idea here is it's an expansion of what's happening here. Here, we don't talk about anything like, oh, there's friction on the train, or there's air resistance, or how strong is the motor. That's what chapters 5 through 8 is. You know, it's like, oh, the motor provides so much force. There's this much drag due to friction, air resistance drag, and there's friction on the wheels and various other things. And now tell me, how long does it take to get to Cincinnati, right? So kind of talking about, you know, what makes the objects move. Or you know how long it took to get there. What was the force applied to the train? Or how much air resistance was there based on the other stuff that we know? All these questions can kind of go both ways. Okay, so that's chapters 5 through 8. I believe that's exam 2. And then the last the last exam is chapters 9 through 11. And this is kind of like, I call it like the conservation section. Conservation laws, where we'll kind of like talk about these things a little bit. but talk about things like interactions between objects. You may have heard of conservation of momentum. If not, now I'm telling you, there's a thing called conservation of momentum. And we can use that to kind of talk about collisions of things. Let's see if I can do this. Oh, yeah, you saw those pens collide? If not, go back to Panopto later, play it in slow-mo, right? But for an interaction like that, you know, like this one is stationary and this one is moving, you know, and that's an interaction between two objects. I'll do it in slow-mo, right? And that's kind of what happened there. So, you know, like there's some, it transfers, the purple one transfers its horizontal momentum to the black one. That's real fast, you know, chapter 9, I believe. And then there's conservation of energy and some other stuff that we'll talk about here. You know, like energy is something that's conserved in our system. Kind of looking ahead, Physics 222 is electricity and magnetism. So kind of different from here. This is all kind of like sometimes called mechanics. So yeah, Physics 222 is electricity and magnetism. And then Physics 223 is waves and optics, right? So we talk about lenses and telescopes, microscopes, all that stuff. So neat. Okay, so that's just, you know, good to know, right? Where are we? Where are we going? We're at chapter 2, one-dimensional kinematics. All right. Okay, so I talked about that. I said kinematics.
Hey.
Oh yeah, what's up? Hey.
Could you repeat what chapter 9 through 12 was?
Oh, 9 and 11 were conservation laws, right? So like conservation of momentum and conservation of energy. Nine through 11, not 9 through 12. I don't know what chapter 12 is. I think we skipped chapter 12. Okay, so in chapter 2, like I said, we're going to stick to kinematics in one dimension, which means it only moves in one direction, right? So for example, this pen falling, right? It only has vertical motion. It does not have any horizontal motion. That's what we'll be sticking to. Now, a cart on a track is, I want to just mention, it's a little confusing. If it's on an incline, here's a cart, or it's on a hill, doesn't matter if it's on a track. This cart sliding down the hill is one-dimensional motion. You might think, well, it has up, down, left, right, but if we call this the x-axis, see how that cart is only moving in one dimension here, right? Now, we'll see this, change your axes, you know, like this is x, someone else could, let's use blue, right? X and Y, kind of like this. Then it does have 2 dimensions of motion, but we're going to be sticking though, we could do this problem this way in chapter 4, but in chapter 2, we're always going to define our axes such that things only have 1 dimension of motion. Cool. You know, start little. Okay, blah, blah, blah. So let's talk about how can we describe the motion of a cart moving with constant speed on a frictionless track. So let's go over here. I'll write that down. Oops. And I think the light is fine, right? The light, yeah, y'all can see that, right? I don't need to turn this other light on. Let's just see if this makes it better. No, let's just leave it off. These are like halogen lights, and they really like heat up the room if I leave them on. It's kind of annoying. Okay, so here we go. How can we describe the motion of a cart moving on a frictionless track, right? So that would be, we can even move over here. Okay, we'll have to look at my messy desk. Don't judge me. It's gonna get cleaner, right? Okay, I'm still putting this like virtual classroom together a little bit. There's like my water, you know, some a level, some pens. But here's a cart, right? Right, so what we have here is that cart just kind of moving on the track. I'll do some better demos later. That was kind of just like happy to see it right there. Okay, now there's a lot of different ways that we can describe the motion of a cart moving on a frictionless track. And I want to talk about some of the different ways that we will, right? One of them is what's called a motion diagram. This is the kind of the simplest. A motion diagram. Now, I think you look in the book and it'll give some formal definition of what a motion diagram is. I'm just going to say, this is my definition. It's the frames of a movie. Right, so kind of the idea here is, whoops, let me make this bigger. Where's my eraser? Right, here's the track, you know, and like we can just kind of like superimpose those frames. Okay, that's enough, right? Superimpose those frames from the movie on top of each other. And in a motion diagram, we generally assume the time between each movie frame is the same, right? I guess you could have a motion diagram where it's not. You'd want to specify that. In this class, they're all going to be the same delta t, right? So that's one way to describe the motion, right? If you're like, hey, you saw this guy moving, you could pull out your phone, make this image, and that would be a really great way of describing the motion of the cart, right? Now, all sorts of things that you can gather from here, the shape of the cart, you could probably figure out how fast it's moving if you know the delta t between these guys. And if you maybe have a ruler down here that tells you the spacing between each of these. So yeah, so motion diagram is one way to describe the motion of an object. Now, sometimes a motion diagram, for simplicity, we'll just use dots. Right? Instead of drawing the cart or the spaceship over and over again, the book will just have dots. And I think they call that the particle model. And just because it's simpler, right? You can just look at these dots to see the motion. Now you lose something. I like the picture better. You can see it's a cart, right? See what's on the cart. Is there a turtle on the cart? Or is there a rabbit on the cart? Or is there nothing on the cart? You lose that with the dots. Also rotation, right? If the cart is like tumbling down the track, that's not going to be represented here. So something to keep in mind. Okay, another way to describe the motion of the cart. You can look at various graphs. Let's talk about the different graphs we can use. Position versus time, right? So this guy here might be a way to describe the motion of the cart, right? Now this is X versus T. Now how does this relate to this guy? First thing, when you have one of these graphs, one of these various graphs, you have to identify your axis, right? So maybe x, positive x direction is, huh? Oh, is it blurry? Oh, maybe if I do this. Okay, hold on. Maybe I do need both lights on. Did that make it less blurry? No? Okay. Let's see. Sometimes just more light helps. So let's see if
That worked.
oh, is it less blurry now?
A little bit, yeah.
Okay. Maybe we'll go like this, right? Might be, yeah, it's better. I know that like sometimes it's the light, you know, because it's like dark, you know, we don't have light coming in. But now it's like, ooh, shadows, right? Yeah, that's fine. Okay, so yeah, position versus time. What was I saying? Oh, yeah. How does this relate to this? Now, here's a few, oh, get back in the frame here. I'll do this. Cool. I think camera is focusing on you. Oh, is that what's happening? I'll stand closer to the board, right? Stand back like this. This is a learning experience too. Okay, now how this relates to this, there's a lot of things I wanna mention when we talk about position versus time. I mentioned one, you have to, you know, identify what is x, right? Is x this direction, or when we look over here, x could be here or here, right? That's an option. But for this guy, I said x is this direction. Another thing that you have to identify is where is x equals 0, right? Notice that's kind of like something that you have to figure out, you know? So like for here, you might say, this is the positive x-axis, and how this relates to this, how the motion of the cart relates to this graph. You also have to include, this is x equals 0 right here, or wherever, right? Now, you could change this, right? Maybe positive x is this way. That might change how this is orientated. You might call this x equals 0. That might shift that graph up and down, right? But whatever you pick will determine how these two are related, right? I said various graphs, but I only drew one, right? There are other graphs that, and we'll talk more about this as we go through. I'm just kind of introducing all this. There's another graph you can use. Velocity versus time. V versus t. Now notice t, right? T is time, right? Not like a space dimension here. And for this one, I'm going to draw this. It's a horizontal line, right? And that's because the slope of this graph of the position versus time is going to be your velocity versus time, right? You should know that maybe from your Calc 1, right? That the derivative of this, I shouldn't say this, the derivative of position versus time equals velocity versus time. And we can kind of see that, you know, in this example, constant slope and positive slope, constant velocity, and positive velocity, right? That's how these two are related. But this graph can also be used to describe the motion of the object, right? Now, if this one is missing something, because this one, you know, it's moving at a constant velocity, you might need to add a piece of information, and at t equals 0, it's at x equals 0 or something like that. Another one of these graphs is acceleration versus time. I'll just put it up here. Well, I'll just, you know, so we know we're just introducing some of this. I'll say Excel versus time. And acceleration is maybe from 151, here, Calc 1. Teacher told you this, maybe, hopefully, I don't know. That acceleration is the derivative of velocity, right? And notice the slope is 0, acceleration is 0, right? And acceleration is kind of the rate at which velocity changes, right? So that's when we start talking about speeding up and slowing down and all that jazz. Cool. There's, whoa, uh-oh. Everything okay? You all still there? I like pushed a bunch of buttons on me. Oh wait, I just need to.
Still here.
You're okay. I hear you. You're still here. There was like almost a disaster here. I'm gonna do a little adjustment real quick. This laptop is like precarious. Okay, are you all still there?
Yeah.
Okay. That was scary. I don't know if you guys just I accidentally pushed the button. Okay. I do want to open the chat back up. Wait. There we go. Okay, got it back. All right. Technical difficulties for a moment there. Okay. Okay, we'll talk about this stuff. Some other ways, we'll put 3 and 4 up here. We can use equations to talk about, what are we talking about? The motion of the cart, right? Or whatever object. We'll definitely, today, I don't think we'll get too much into equations. In the video I make and post on Panopto later, we're still recording? Yeah. I'll start talking about equations. Today we're gonna kind of stick to how these things are related. But I'll just put an equation, how about, I'll just make one up. X equals 5t plus 1 or something like that. Now, I do want to mention this about equations. Here's my dealio here. Let's set this down here. You got to put what these variables are. X is distance to the right from start point. In centimeters, let's just say, right? You always want to, you can't just, the equations by themselves have no meaning unless that's kind of my point here, define what those variables need. Oh, T, we got to say that. T equals time in seconds, maybe since start of motion.
Sorry, can you repeat what X is?
Oh, distance to the right from start point in centimeters. Cool. I mean, for this one, right? I mean, it doesn't really matter what it is, but the point being should be defined, whatever it is, right? Cool. And like what we have here, I should have put, let's add something here. Make this look better. Various equations. Kind of like there's various graphs, there's various equations, right? Because you can have x equals something. You can also have v equals, I'm just going to write blah, right? Blah. I'm not going to make up an equation here, right? You can have a equals blah, right? Acceleration might be given by an equation, and there'll be some relation between acceleration, velocity, and position, of course, right? Okay, so that's another way in which We could describe the motion of the cart moving on a frictionless track. And then the fourth one, I'll put, is this one, doesn't take up a lot of space. We won't do it too much. We can just say in words, right? You can just say the cart was moving to the right at 15 centimeters per second on the track, right? Just describe it in words. That's another way that we can describe it. All of these have different relations to each other, right? And that's going to be a lot of the focus of chapters 2 and 4 is just how all of these relate to each other, the motion diagram to the graphs, to the equations, to the words, and so forth. And kind of like there's also relations between the equations and between these graphs, right? So we'll talk more about that. But those are the 4 main things that we can use to describe the motion of a thing, kinematics. Okay. One thing I want to do a quick definition. Let's go back over here. Here's that cart. Look at all those shadows. That's kind of cool. My morning class isn't as shadowy. Okay. I want to talk about one thing. Maybe you've heard this before, maybe not. Speed versus velocity. I do want to mention this. This comes up. Right. So speed is kind of like, let's do kind of first of all, I'm just going to say speed is always greater than or equal to 0. And velocity can be positive or negative. Right? Velocity can be either positive or negative. Now, velocity is kind of like, velocity is a vector. And speed is a scalar. Right? And speed is kind of just the magnitude of velocity when you think of velocity as a vector. So when I throw this pen into the closet, it has a velocity of, 5 meters per second towards the closet, right? But the speed is just 5 meters per second. Oh, there's a question, what is the relation of acceleration? For now, don't worry too much about it. We will talk a lot more about acceleration later. But what I did say was acceleration is the derivative of velocity, and acceleration is, or in other words, acceleration is the rate of change of velocity. But we'll definitely talk about that more maybe today. I think so. But, anyways. But yeah, speed is kind of like the magnitude of velocity, right? If the pen is going this way, you might say it has negative 5 centimeters per second. It's going this way, it's positive. The positive or negative indicates the direction, right? But speed is just kind of like the total speed, right? So it's just kind of like, sometimes we say speed is the absolute value of velocity. And one good illustration is an object in circular motion. Oh, do I have I have a piece of string here. Oh, I have a webcam, this will work. Cool. This webcam's busted anyways, so we'll put it to good use, right? Here's a webcam. Maybe I think it can be fixed, but for now its best purposes as such, right? I'm spinning it around here. Now I'm spinning it at a pretty constant rate. You know, you can see like, duh, 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 duh. Now, the webcam has a constant speed. It's always moving at the same speed, right? You can kind of see it spinning there. The velocity of that webcam that I'm spinning around is constantly changing. And that's because, remember, velocity, I said, is speed and direction. You know, at some point, it's moving this way, then it's moving this way, this way, this way, this way, this way, this way. And it moves around the circle, right? So it's changing direction means it has changing velocity. Changing direction does not affect the speed. And so that's just like a good example or illustration, I think, to kind of relate those two. Okay, I'll put this down carefully because I don't want to further break this webcam. Actually, I think it's just the cable that's broken, which is, I guess, what I was messing with anyways. All right. Let's skip that. Okay. Okay, we talked about that. I'm just kind of looking through. Oh, we did talk about that. Okay, let's talk about speeding up and slowing down. Kind of related to this. Let's erase this. Also, I'm going to post this on Panopto, like I said. But something's up with Panopto right now. So it might not upload until tomorrow. So just kind of keep that in mind. I don't know what's up. I got an email that they're having issues. So with their like server or something. Okay, speeding up and slowing down, right? Okay, I'm not going to write this on the board. Speeding up, speed is increasing. Slowing down, what do you think slowing down is?
Decreasing.
Yeah, all right. I'm not going to put that. Speed is decreasing, right? So that's the idea here. Now, what I'm going to put up on the board are 4 graphs, and there are 4 velocity graphs. Oh my gosh, okay, and the units don't matter, these are unitless. Okay, 4 possibilities I kind of drew. You know, 2 of them have positive slope and 2 of them have negative slope. 2 of them are positive velocities and 2 of them are negative velocities. And I'm going to tell you, 2 of these are objects that are speeding up, and 2 of these are objects that are slowing down, right? And so what I want you to do, I'm going to put you all, if you want to screenshot this real fast or just copy it down, it's fine. But I'm about to put you all in the breakout rooms. I'm going to make groups of 5, and I want you to discuss which ones are slowing down and which ones are speeding up, right? And there's 2 and 2. And then we'll come back and see what we think, right? So, okay. I'm going to hit pause on the record first. It's so weird when that thing talks. Okay. I heard a few folks have some different things. I didn't make it to all the groups. But out of the groups, I heard kind of 2 different philosophies, so to speak. Yeah, that's good enough. Some folks said this. Let's label them. I'll just call it A, B, C, and D, right? Just so we can point them out. Some people said these 2 were speeding up, and these two were slowing down. And the reasons I heard were positive slope, speeding up, negative slope, slowing down. Now, some other folks said these two are speeding up, and these two are slowing down, right? So A and D speeding up. I'll write it like this. This is maybe a little more clear. And the B and C is slowing down. And I think those are generally the things that people think. And I'll tell you that, I'll just kind of say the answer because we should take our break in a minute. This is the right answer. Speeding up and speeding up. And some people might say, what? The slope is negative. It looks like it should be slowing down. But remember that speed and velocity are different. The velocity is decreasing. But what is happening to the speed? For this one and this one, they both start off at like, remember, speed is magnitude of velocity. They both start off at like 10 miles an hour, right? Speed is absolute value of velocity. And then what happens to the speed? It becomes 20 miles an hour at some later point. 30 miles an hour at some later point, right? The thing is speeding up. These two, it's a little easier with these two, I think. These two are slowing down because what's happening to the speed? The speed is trending towards zero. If something's speed is going to zero, that means it's slowing down, right? And the two examples would be something, it's initially going fast and slowing down like this. And then the other one, whichever way your axes are, fast and then coming to rest, right? Because at some point, if you continue this graph, is that fair? At the intercept, V equals 0, and that's stopping, right? So slow down, speed up, speed up. Now someone mentioned something, and we'll talk about this. The derivative of this is the acceleration. Velocity is positive. Acceleration is positive. When the signs of velocity and acceleration are the same, that means it's speeding up. That's what's happening here too. Velocity is negative and acceleration is negative. Notice the y values are negative and the slope is negative. So same sign, speeding up. Mixed sign, positive velocity, negative acceleration. Slowing down. And then the last possibility, what is this? Velocity is negative, acceleration is positive. Also slowing down. I'll write this down so you can copy it down. Accel and velocity, same sign, speeding up. Opposite sign, slowing down, right? And that kind of makes sense. Man, I wish I had a bigger room. Anyways, we'll use the tortoise here. It's always good to have a little demo. If the tortoise, let's say tortoise is over here, this is the positive x-axis, right? So positive velocity is this way. If the tortoise is going this way, velocity is positive and acceleration is in that direction, what's going to happen? Turtle's going to speed up. What happens if the turtle's going this way and acceleration is opposite? Turtle is going to slow down, right? Velocity positive, but it accelerates this way, it comes to a stop. That's kind of why the mixed signs mean slowing down, same signs as speeding up. Cool. All right, it's 7:11. let's take just like a 5-minute break. I'll push stop on the record. Man. All right, two of the settings I gotta look up. One, turn that doorbell off. I don't know if you all can hear the doorbell every time someone comes in and out. Don't worry about it if you come in and out, it's fine. But I gotta figure out how to turn the doorbell off. Someone turned the doorbell on over summer. The other is the focus thing. It sounds like it's focusing on me, which is of course very important. But I think we'd rather focus on the board. Okay. Look at me enough. All right, so let's try this. We had one thing. The cart is initially at rest at the top of a hill. Top of the ramp, maybe. And let's call this x equals 0. And we won't worry about the units or anything, values, but I'm just going to, let's crap. This is whatever that is. And now what I'm going to do, I'm going to put you all in the breakout rooms again. And what I want you to do is just make a quantitative sketch of x, v, and what you think the acceleration is going to be, right? So just kind of, doesn't have to be exact, right? But just kind of like an estimation of what you think. Your options are going to be either lines. I'll give you this. So, here's all the options. Increasing line, decreasing line, horizontal line, concave up, concave down, right? So just kind of stick to stuff like that. Don't have to be like concave up exponential or concave up, whatever. Don't worry too much about that, but those are kind of your 5 options, right? Horizontal line, slope increasing line, slope decreasing line, concave up, concave down. And all right, I'll do the breakout rooms. Give you a moment. I'll maybe jump in a breakout room or 2, and then we'll talk about it. Yeah, gotta find.
You're muted.
Thank you. Yeah, I'm now, I answered all the most important things in that last second there. You got it all right. You read my lips. Answers to all the questions on the test. No. So with this guy, I heard some good stuff. Going through those chat room box things. So a few things, right? We know that this is x equals 0, right? That's its starting point. And the cart is initially at rest. So those 2 things kind of tell us something here. This is kind of a challenging one, but if it's initially here and the cart is initially at rest, I think whatever these graphs are, it's going to start at x equals 0 and velocity equals 0, right? Now something we haven't talked too much about, but maybe you know, but I'll kind of tell you now. But objects that roll down ramps or that fall have constant acceleration, right? So, and I'll talk a little bit about this, right? An object that falls with no air resistance whatsoever, if, I suck the air out of this room, and you're on Earth's surface, we say that things accelerate downward at 9.8 meters per second. Squared. And sometimes we just call that G. That's the variable, right? Now things that go down ramps, there's going to be some trigonometry involved. We'll get to that when we get to chapters 3 and 4. But I do kind of want to mention that, right? So there'll be like, you could do your SOHCAHTOA thing here if you knew what this angle was, and assuming no friction. But for now, we'll just be kind of qualitative about things. But there's a little bit looking ahead for when we do start talking about the equations, right, I mentioned earlier. Okay, so that being said, is the acceleration going to be positive or negative? I think I heard most of the people say acceleration is positive because it's initially here and it's going to accelerate down the ramp. So this guy is going to be a constant, something kind of like this. Now velocity is going to be increasing at a constant rate. And the reason is, why is it constant instead of concave up? If acceleration is constant, velocity is a line, is linear, right? And that's because of those two properties. The slope of velocity has to equal acceleration, right? This is a constant, then this has to have a constant slope. Now, there's a lot of glare. We'll fix that. Now, that property is going to be true this way. Just getting my words here to make sure I don't say this backwards. The velocity is the derivative of position, right? And so what that tells us is the velocity is the slope of the position graph. Now what's happening here? Velocity is increasing. What should happen to the slope here? The slope should also be increasing. And that's why this one is going to end up being concave up, right? And that kind of makes sense because notice at first it moves kind of slow. The slope is pretty horizontal. And then the slope increases as it speeds up down the ramp here. So that kind of makes sense. Okay, let's try this same thing. And I won't do the whole breakout room thing. But let's change the situation. How will this look if the cart is pushed up the ramp? I have the cart and the ramp. We should be doing this, right? Let's set it up. I'll set up the cart and the ramp. The cart always needs a passenger. What should the cart have as the passenger? You should meet the mascots, right? There's here we go, the turtle and the hare, right? Which one should be the passenger for this example? Turtle, tortoise, or the hare?
Turtle, tortoise.
Ooh, throw it in the chat. We'll go with the vote. Whatever is more will be the winner. 1 for tortoise. I'm going to just count down from 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. It's the tortoise. Okay. The tortoise will be the passenger. All right, and then let's move this over here, right? And we'll just do a quick setup. It's a little disorganized now, but things will get a little better here. So the first example we did was what? Tortoise is on there. Cart is initially at rest. The x-axis is this way. We let go, and that cart slides down the ramp. Now, in this example, what we're going to do is we're going to try and draw the same three graphs: position, velocity, and acceleration. If I push that cart up the ramp, right? And our turtle has survived, right? One more journal, or one betrayal, right? I don't know what that's about. Okay. So let's try drawing this in this situation. We'll just kind of think about it together. I won't do the breakout rooms. So position. I'll do them this way: velocity and acceleration. Now, something we got to do with this ramp. I'll just draw the ramp over here. Here's the ramp. What are we missing before we can do anything with this problem? We actually are kind of like, it's not possible until we do one thing first. Two things, technically. You could call it one or two things, depending on how you think about it. We got to define our axes, right? What is the x direction? Is x go, and that's important, right? Is x this way or is x that way? Either one of those could be done, and maybe we'll do both. Let's try both, right? Let's actually do both, right? So here's what we'll do on the fly here. In purple, let's do x in that direction. And the other thing that we need to kind of mention is where is x equals 0? I'm going to call x equals 0 the bottom of the ramp, no matter what. I'm just going to call x equals 0 the bottom of the ramp. And then what we'll do for fun, let me get another color. Blue is just so similar. Let's get a green here. And they'll both have x equals 0 here. But in green, x is positive in the other direction. And let's try both ways, right? You know, and either is fine, because this could be a lab station, right? And I might be sitting at that lab station saying positive x is to the right, and someone else is standing on the other side of the lab station and say positive x is to the right, right? So it's all relative to each other. Okay, now let's go with the purple one first, and I'll just draw both. Let's draw both graphs on the same thing, you know, purple and green here. Okay, now the cart starts at 0 right here, right? So I'm just going to do this. Cart starts right here at 0. Now, what direction? I kind of always like to start with acceleration, velocity, and position, kind of like this. You can go the other way, it's fine, but let's start with acceleration. Acceleration is constant. And now I'll ask you all, you can say out loud or throw it in the chat. Is acceleration going to be positive or negative for purple? Positive. 1 for positive. 2 for positive. 3 for positive. Any for negative? Going, gone. Lamb got positive just in time, and that is correcto. Positive because, is that fair? It's accelerating down, the cart will accelerate down the ramp. So let's just do that and say, right, there is Yeah, maybe what I'll do, because the color turns out too well. Ooh, there we go, right? So like with the dashes, right, that just kind of accentuates it more. So you don't get it confused with the axis. Okay, now here's a tricky one. Velocity is kind of the hardest one. Is velocity constant or does velocity change? What do you all think? Any guesses? C for, I think C for changing. Oh wait, I guess constant starts with C. But yeah, it's changed, right? Feeling, right? It's changing. Now, is velocity initially positive or initially negative? Yeah, changing in the positive. It's changing because acceleration is non-zero. Now, is velocity initially positive or negative? Right, who's the tortoise? Carmen says negative, and Carmen is correct. Initially negative, and the reason is positive x direction is this way, velocity is initially this way. Now, what happens to velocity? As the tortoise goes up the ramp, velocity comes to 0. The tortoise stops for just one moment and then goes down the ramp. So what I think this corresponds to is velocity, as Carmen said, is initially negative. I think it's going to look like this. I'll put an arrow here, right? And the reason is, right, initially negative, and this is a line because this is a constant, right? It's changing at a constant rate, right? And so what does this point represent? This is the point where the tortoise came to a stop at the top of the ramp. Velocity was like, you know, going up the ramp, came to a stop, and then started heading down the ramp. And notice this is where velocity switches to positive, right? Because that tortoise goes now positive velocity down the ramp. Okay, now one more. We got one more. This is cool. Up here, position. What's this graph going to look like? This is going to have to be some sort of now, is it going to be concave up or concave down? Ooh, put your votes in the chat, right? We know it starts like this, but is it going to be like this, or is it going to be like this? Concave. Now, keep in mind, concave up, yeah, is like up like a cup. Concave down is like that. But Cody got it. It's concave up, right? Now, I'm going to be careful here. Okay, now it's concave up. Now let's talk about why it's concave up. What is the slope right here? The slope is negative. Negative. Slope is 0 at the minimum. 0. Slope is positive. Positive, right? So that's one way these graphs are connected, right? That's one thing I want to mention. Another thing, now let's talk about what the tortoise actually does, right? Here's the, was it the tortoise? Yeah, the tortoise is right here. If x equals 0 is here, and we said the positive x-axis is that way, take a look. This should be like x equals -1, whatever the units are, doesn't matter. Meters, centimeters, Doesn't matter, right? Notice that -1, -2, -3. And then down here is what? +1. +2, +3 going down the ramp. That's why it's initially going down and then back up. And this is the return point, right, where it comes back to the start. And then, like I said, right, crosses the t-axis and the 0 here, right? Okay, one more thing before we draw in green. Where is the turtle? No. Where is the hare speeding up and slowing down? Now, let's look at what's happening here. The hare went up and then back down. While the hare is going up to this point here, is it speeding up or slowing down? On its way up. Any guesses?
Slowing down.
Yeah, right? Because I've given a push, and then what happens? Velocity goes to 0. And that's consistent with what I see right here. Because take a look. What did we say before? Acceleration is positive. Velocity is negative, right? Velocity and acceleration are opposites of each other, which corresponds to slowing down, right? And then what happens after the hare is at the top and starts slipping down that direction? Velocity is now positive and acceleration is still positive. And what does that correspond to? Speeding up, right? So it kind of matches what we were saying before. Cool. Let's do this. Let's do the green deal, and then we'll talk about some other stuff, whatever that piece of paper says. I need a little water. Okay. In green. Now let's do all of this. Now let's start at the bottom and work our way up. In green, what's acceleration? That fair, it's negative, right? Because this is the positive direction. Acceleration is opposite, right? So we got a negative here. And then what's going to happen? It's kind of like reversing. Is that fair? Starts off with a positive velocity. It gets 0 sort of at the same spot. And then here. And then I guess it's just a mirror reflection. Ooh, that's pretty, right? That's, look at that symmetry. Parabolas, lines everywhere. Pretty cool looking. But that's what it would be like keeping that same x equals 0 stuff. Okay, what do we got next? Let's find out. I have no idea. Oh, man. Like, said all of this. Okay. Now, one last thing that I want to get to. This may be new, maybe not. We've talked a lot about slope. Let's erase the green for now. I don't care about the green anymore. Let's focus on the purple. And it's distracting, right? That. Yeah, I'm good at erasing. I should make erasing my job. Technically, right now, erasing is my job. Wow. Okay. All right, look at that. Okay, that's pretty good. So we got the green and I got rid of that horizontal line here. Now, something that we talked about and should be familiar with is there's this relation of slope, right? Velocity is the slope of the position graph. I'm just going to write that right there. Let's get rid of this. All right, velocity is the slope of the position graph. Oh, I'll just write this one too. Why not? Acceleration is the slope of the velocity graph. Cool, right? We talked about that, right? Acceleration is the rate of change of velocity. Velocity is the rate of change of position. Now, there's another relation that then this might be new. I don't know, depends what you've done in your life. And it goes in the opposite direction. Now notice these are always at a point, right? You're like, at this point, the slope is 0. At this point, velocity is 0, etc. Now, for this next one, we have to talk about intervals. Okay, so the area under the velocity graph is the displacement or change in position. I'll just say is the change in position. Same thing, just one less word. All right, maybe this is new, maybe not. Give me a cool grid here, right? So what does that mean? Now, for now, we're just going to be qualitative, and then we'll be quantitative later this week, or in the video that's not live or whatever. Make the video, I guess. So area under the curve. Now, keep in mind, these are always instantaneous values. Like I said, instantaneous. These are intervals. Area under the curve requires that you talk about an interval. And so you can look at any interval that you want, just like you can look at any instantaneous value. If I look at this interval, what kind of area under the curve do we have? We have a positive area under the curve. And if we had like units and stuff, this area would represent this change in position. Notice it's a positive, oh wait, we should just do this. Notice it's a positive change in position. I'll talk about why this is later. For now, I'm just telling you so you're familiar. It's kind of nice just to be familiar with something and then learn why later sometimes, right? But so notice positive area, and we go in increase in position. Now, what about this area that I'll put in green? This interval, what do we have? Is that there it's negative area because it's underneath the curve? And what do we have? We have a decrease in position. If I were to do both of these together, they cancel out, right? Same area here, same areas here. And what's the change in position? Nothing, right? Kind of works out like that. And then this same thing happens at the next level. Area under the acceleration graph. Acceleration is the change in velocity. Now this one's kind of weird because the area graph is a constant. Notice though, let's just take an interval. This area is represented by this change in velocity. Or maybe it's a little less. Right? See how from here to here we have a positive area and we have a positive change in velocity here. Okay, so maybe that's new, maybe not, I don't know. But it's about 8 o'clock here. So what I'm going to do is I'll hit stop on the record in a sec. I'll first though ask if there's any questions about anything, specifically because this is the first day, right? This is our first day of class. Logistics, you know, like, did anyone have trouble like doing the mastering or whatever like that? Or like, what's going on? I will say on Monday we're going to have a lab. It'll be on this stuff here, right? And then the next Monday's lab will be this stuff here, but quantitative. The lab on Monday, kind of like this, where there's like pictures and drawings and things like that. It's from the tutorial book, this blue turquoise one, first edition. And I think the pages are in the calendar. I think it's pages 11 through 14. And our labs during class time, yes. So you have to come during class time, and I'm gonna make some lab groups that you'll be working with. And what I'm gonna do for lab groups is you're gonna be in a lab group. It'll be the same lab group for 2 labs. So you'll be in the same group 1 and 2, and then I'm gonna mix it up. You'll be in a different group 1 and 2. So kind of change things a little bit. I just randomize it, just make it pretty random. But yeah, you definitely have to come. Mandatory. I'll be floating around between the breakout rooms, answering questions, and then you're going to turn in what you have from the tutorial thing, and then you'll have to do the homework from the other book due the next week. So cool. Well, this was fun. Did you all have fun? Was this, you know, do you enjoy yourselves? Are you liking physics so far? Yes. I heard 1 yes. Oh yeah. All right. Woo. All right. Loving physics. Okay. Yes. Yes. All right. Yeah. Just took that first person to say it, and everyone else, you know, chimes in here. All right. So I haven't heard any other questions. I feel like I'm just now like dilly-dallying here. So I will close this, you know, Zoom thing. And like I said, something's up with Panopto, so this might not get uploaded till tomorrow. It'll just sit on my laptop all night. I don't know. We'll see. And yeah, I will see you all on Monday. And at some point tomorrow or Thursday, another video will show up on Panopto, right? Kind of doing this, but with numbers and equations and stuff. Right? So we did the various graphs. We'll look at the various equations. All right, cool. Check you all later. Go Seattle Central Tigers.